All right. Hello, everyone. So, yeah, unfortunately, I'm missing the cable that normally connects my laptop to here. So we're gonna do things a little funky. It's gonna totally work. I'm gonna just have the live stream on the main computer. It's the same thing, so that should work. Obviously, it doesn't like that I'm logging in here though. So there'll be a slight delay, but that's fine. It is workable, assuming the internet all works and all that. Good things there. So, yeah, 1.5 weeks ish till your first test. It is coming up. You know, time keeps on moving, right? So remember, y'all's test is February 18th. February 18th and February 20th. Wednesday, February 18th. Friday, February 20th are the days of your all's exam. Wednesday will be the multiple choice. Friday will be the free response. The multiple choice will be if it's not 2-point charges, if it's a charge in a field, you're going to use this top one. And you're all going to notice, if you look at the practice test, there's a problem that makes you do that integral. Now, all these integrals are super easy. Like if you're going to see today, what we're going to do today are Calc 1 level integrals. All you need to ask yourself is what is causing the field, and what is the equation for that field? And there will be an equation for it. We'll do the integral. Okay, so that's kind of where we did it. And then the last thing we talked about was, hey, what if you have multiple charges? And if you have multiple charges, you have to build the energy of the system. You have to build the energy of the system. So in this problem, we built this system. We had one charge that took no energy to bring in. To bring a second charge in, it took KQ1, Q2 over R. To bring a third charge in, it had to fight the other two. So that one was an extra K1, Q2. You got two more terms, and if you add them all together, you equal 3. For this, I think this is worthwhile. I'm going to make a new question here. See if you all made sense of this. The following system has 3 charges in it and has an energy given by, we did this last class, 3kq squared over r. That's what we did last class. We found that. If I brought a 4th charge in such that it was a distance r away from every other charge, what is the new energy of the system? Okay, so this is my question for you all, and I'm going to go ahead put some answers here. 3, 4, 5, 6. 0 is hopefully obvious, it's not that. Let's maybe jump up a bunch and go to 9. Yeah, 0 wouldn't make any sense. Don't do that one. All right, then I double check on my plugs. So while you're looking at this, same problem as before. What's the energy if there was 4 charges instead? And this is really going to check if you actually understood what we did last time. The last thing we did, at least. I'm really glad I asked this question. Let's put it that way. same value of charge. They're all Q. They're all Q.
Yeah, that's what I mean.
Does not mean it has the same energy. Yeah. I just put that because you're saying you realized that I needed that information. All right, give you all about 20 more seconds. The math here is not hard. All right, and 5, 4, 3, 2, 1. All right, so if we want the energy of the system, we need the energy to bring in one charge, plus the energy to bring in the second charge, plus the energy to bring in the third charge, plus the energy to bring in the fourth charge. That's what we did last time, right? These first three terms we already did. This is kq squared, 3kq squared over r. We did that in the last slide. I'm not going to redo it again. 3kq squared over r. So really the question is, how much energy is required to put a fourth charge, and this is very hard to draw, but it's a distance r away from all these. It's not on the page. It's like, a pyramid shape. Yeah, the only way for it to be a distance r is it needs to be three-dimensional. Just geometry-wise, it's what it has to be. All right, to bring in this charge, how many charges am I quote-unquote fighting to get there? 3. It is having to fight 3 charges to get there. If this is 1, this is 2, this is 3. So the energy for 4 is kq1 q4 over r plus kq2 q4 over r plus kq3 q4 over r, which they all have the same. So this ends up being 3kq squared over r. So by adding one more charge, I didn't make the energy just go by 1, I actually doubled it. Why did I double it? Because every time you bring a new charge, it has to fight, quote unquote, all the ones before it. And you still have the energy from before. So my new energy of the system is 6 kq over r, because it's both of them together now. So this is the idea of the system. You get more and more, every single charge, you get more and more energy. It requires more and more energy. But in turn, you store more energy. You store more energy. If you released this fourth charge from the system, that potential, just that one term, would get all kinetic converted to kinetic. If you release just that one, all of its energy would get converted to kinetic. The rest of the potential energy of the system would stay there. The other 3 charges that are fixed in place, that would stay there. If they all got released, then all the energy gets distributed to kinetic. Okay, so that's just making sure that makes sense. All right, so let's look at this problem. An electron is released from rest a distance z above a charged infinite plane with a charge density given by sigma. What is the speed of the electron just before it hits the surface? Use QE for the charge of the electron and M for the mass of the electron. Okay. That's crazy. So what are we solving for? We're solving for V. We then draw a picture. Here's my infinite plane. Presumably it's a bunch of positive charges. Otherwise, this thing's not going to get attracted towards it. Then you have your negative charge up here, a distance z away. And the question is, how fast is it going to be right before it hits it? This is like the water balloon problem I gave you at the beginning of last class. This is just like the water balloon problem, except instead of gravity, it's an electric field that's pulling it down. How did we solve the water balloon problem? What concept from Physics 1 did we use to solve that? We used work and the big old kind of putting it all together, energy, conservation of energy. Specifically, we used that the change in potential energy equals the negative change in potential equals the change in kinetic. If you're looking at this and saying, how is that conservation of energy? This is, if I could write it this way if you want, just to show you all, these are the exact same things that you're used to seeing. These two statements are the same. Negative change in potential just means instead of final minus initial, it's initial minus final. If you'll rearrange this equation, you get U initial plus KE initial equals U final plus KE final. That's what you all have traditionally seen as conservation energy, but this thing at the top is the exact same thing. It's just written condensed. They're the same expression. I just did algebra. So, in this class, especially on test 1, if I ask you to find the velocity of something, you're going to use conservation of energy. If I ask you to find the velocity of something, you're going to use conservation of energy. Or if velocity is even mentioned in the problem, you're going to use conservation of energy. Why? You could do this with forces, but you'd have to, well, we're still going to have to do an integral. This is easier to help you understand than doing an integral. We end up integrating force anyway, but whatever, that's fine. So, I'm going to use this top one, because it's easier for me to kind of connect the pieces. Yes, the bottom one is the same, but the top one's going to be easier for me to explain this to you. One of our slides has an equation for the change in potential energy. Kinetic energy is easy. You all know that. 1/2 mv squared. Like that hopefully you all know. If you don't, good to remember. Oh, look. The change in potential energy. Now, there's 2 equations here. Which one do I use? This one is if I have 2 point charges. This one is if I have a charge in some field. If we look at our problem, which one is it? The first one. An infinite plane is not a point charge. It's not a dot. You all can see that it's not. Hopefully clearly. So we're going to use that this negative change of potential equals the integral. So Q integral of E dot dr. If you're like, where did the negative sign go? Both had negative signs, so they canceled. If you want, I can write it with both negative signs. There's a negative and there's another negative, so they cancel. This one says negative change of potential. Well, it turns out the change of potential equals a negative, so they cancel. So that's the left side. Equals. The right side is hopefully something you're cool with. It's just kinetic energy. 1/2 mv squared. And I'm just going to subtract the velocity squared because it's change. M is the same, factor now, all that good stuff. 1/2 mv final squared minus 1/2 mv initial squared. What's my initial velocity in this problem? Boom, that second term goes away. So now in this Q at the front, that is the charge of an electron, because that's the one experiencing the field. So the question is, what is making the field? And I'm going to give you all a few moments to think about that. What is causing the field? And, bonus points we didn't get, this is what we actually need. What is the equation that gives us that field? It is something we derived in a previous class. So I'll let you all kind of look through and see if you can figure it out. All right, so what's causing the field? What object, what thing is causing the field? The plane, the infinite plane. The infinite plane was one we solved last time using Gauss's law. To remind you how you solved that using Gauss's law, you drew like a cylinder that goes through it. And then I'm going to move this V equals question mark over to the side somewhere. I am not going to have enough room. I'm going to totally steal all this and move it over to the next slide. I'm going to derive it in like 3 lines. It's not a hard derivation. Once you know the right Gaussian surface, make sure you all are practicing your Gauss's law. It's notoriously one of the things we all have difficulty with. Gauss's law, integral E dot dA equals Q enclosed over epsilon naught. The area here is going to be the area of the top and the bottom. So pi r squared plus pi r squared. My Q enclosed equals sigma times pi r squared, because the Q enclosed is the Q enclosed by that over epsilon naught. So you get E equals pi r squareds cancel to epsilon naught. This is a very useful equation to know. And there's something really interesting about it that we talked about. Do you all see distance anywhere in this equation? No, that's going to be really nice for us when we're about to do an integral. So we're now going to take this electric field, and that is the electric field that's going on here. So we're just going to take this and put it down here. So we get the charge of an electron times the integral of sigma over 2 epsilon naught. Remember, this is a dot product, so it's dr magnitude times cosine theta. In this case, I'm just going to tell you the way that we write this dot product is such that E is in the radial direction, R is in the radial direction, so this always ends up being 0. Cosine is 0, which is 1. That pretty much just always happens with this integral. You can pretty much always ignore that. Okay. And that equals 1/2 mv squared. mv final squared. dr is distance. What are the bounds? So what are we going to we can leave it as dr, I guess that's fine. Where do I start and where do I end in this problem? Where's my starting position and where's my ending position? So yeah, where does my object start? I heard the bounds. I think we're going to start at z, and we're going to end at 0. So it's got to be backwards. All right. Sigma, constant. 2, constant. Epsilon naught, constant. Pull them all out. So you get QE times sigma over 2 epsilon naught. What's the integral of dr? R. In this case, though, it's just going to be evaluated from z to 0, so one of them turns into... Oh, and there's a negative sign here. I'll be kind and put this. So, so much space. All right, so we're going to move this up, give myself a little bit more space. This still equals 1/2 mv final squared. So this just turns into Q, actually a negative sign. QE sigma over 2 epsilon naught z equals 1/2 mv squared. Okay, now you just solve for v. So VF is going to equal the square root of 2 times QE times sigma times z over 2 epsilon naught. And there's an m on the bottom as well. And there's a negative sign here, and you might look at that negative sign and say, oh no, we can't take the square root of negative. What's the charge of an electron? It's negative, so they cancel out. So if you want, we can just kind of get rid of this E and then get rid of the negative sign. Yeah, and so it's a Q of an electron, and then you would just plug in the numbers and get, that there you go. But there are no numbers here, that's the answer. That's beautiful thing about time numbers. You don't have to plug it in. I know this final expression looks complicated. I know that, and that's why you don't look at the final answer and say, you never look at a problem, look at the answer and say, yeah, that makes sense. That's basically like looking at a computer and looking at the CPU on it and seeing all the transistors and being like, yep, I totally understand how that works. A computer is incredibly complicated, but every individual step that gets to making the computer, you can break it into small enough pieces that it's not. And that's something to remind you all of. You're going to build and make very complicated things. The final product will be very complicated. But the goal is that each individual step you took to get there was not. That's the mindset you want to get in. And that's how you don't get intimidated by these. So, let's recap what we did. It was conservation of energy, something you've hopefully done a lot. Kinetic energy was 1/2 mv squared, something you've seen a lot. The only new thing here was you had to get the potential by doing an integral. In this integral, you needed to remember that one charge experiences a field, the other makes a field. What makes this field? The plane. What's the equation for that? Put it in there. Do the integral, and then math after that. So really the only new thing here, physics-wise, was realizing this potential now has a new expression. It's not just mgy. You have to maybe actually do the integral. Remembering what the electric field is for an infinite plane, and then after that, it's just math. The only new physics here was this equation for potential and the electric field for that. And then after that, it's all math. You've done conservation of energy. You've done kinetic energy. You've done integrals, but that's more math thing. So don't get too overwhelmed, but this is, it is a bunch of steps strung together. We had to build it. There was not just an equation that said V equals and you plugged in things. All right. So, great. That's energy. That's as complicated as energy will get. And, I do need you to be able to do these integrals. I do need you to be able to integrate the electric field. You just need to choose the right electric field. That's really the only challenge there. If I say find the energy and you're in some field, choose the right field and integrate it. Okay. Now, moving on to the next piece. This is what we're going to be spending Monday and Wednesday next class on as well, and then Friday we'll get to capacitors. Previously, we asked what causes electric forces, and we made up fields to explain it. There's two charges, they cause a force, but why? They're not touching. There's this thing called a field. Now, we can ask ourselves, what makes this electric potential energy? And the analogy I'm going to give you is I'm going to keep referencing the Earth. And this is actually, if you're in the Physics 2 labs, this comes up in it as well. Is there any potential energy right here in space? Ignore that there's air here. Oh, yeah. Ignore that there's air here. Is there any electric, for those online who can't see me, I'm gesturing to the empty air. Probably not. Is there any energy stored here? Ignore the air. Ignore the air. No, right? Like, can I get this energy out if there's no energy there? How do I know there's no energy there? There's nothing there. That's the point. There's nothing there. What do I need to put there to get some energy? How do I get potential energy? Yeah. You got to put a mass there. I don't care what the mass is. There's no energy here, but when I put this mass here, now there's energy. Here's the idea. Even though there was no mass there, there was this hypothetical ability for there to be energy. I just needed to put a mass there to actually get that energy. And as I go up, do I gain more energy or less energy? I gain more energy because did the mass change? No, what did change? The height. So, there's this idea, this is the idea we're going to be using here. That the Earth, I'm going to reference the Earth for now. This is gravity. It's not what we're going to be talking about, but you understand gravity, so we're going to lean on it. The Earth makes a potential everywhere. A potential. There's no energy there. There's a potential. And as you get farther from the surface, that potential increases. Then when I put an object there, now it has energy. The higher that potential, the higher the energy. The higher the quote-unquote height. The higher the energy. We're going to use the same idea here. One charge is going to make something called a potential. Another charge will experience that potential, and that's how you get energy. And we call this potential voltage. This is called electric potential. It's also called voltage. So I can write this another way, and I can write this one another way. Remember how the field, you put a charge in a field and it experiences a force? If you put a charge in a potential, now you have energy. Just like when you put a mass in the Earth's potential, now it has energy. When that mass wasn't there, there was no energy there. So the idea is one charge makes a potential, the other charge gets an energy from this potential. Well, the whole system does, but that's the way we're going to phrase it. Okay? So it's a kind of a funky idea. I know, but once it clicks, like anything in life, that'll make sense. Could you say that? Yeah, so one charge is going to make a potential, and when you put another charge in that potential, now you'll have energy. And you all saw this in your physics labs. You all did an experiment where you measured the voltage, and in fact, this is the experiment this week, maybe you haven't had it yet, where you measure the voltage between 2 point charges. And you all made a graph that looked like a hill. You all made a graph in your labs where you measure the voltage. You had a positive, quote-unquote, positive charge and a quote-unquote negative charge. And you all made a graph, and it kind of looked like a hill that went downhill. That was my height. There's no energy stored in that system, right? Like, that just shows you the potential. Here's the idea, though. If I have this height map, and I put a positive charge on a hill that goes down, what's that charge going to do? Which way, if you put a ball on a hill, what's it going to do? It's going to roll down. You can think of that hill as a difference in potential. At the high point, there's a higher potential. At the low point, lower potential. You put a ball in it, higher potential energy, lower potential energy. Same thing with this voltage. It's a hill. At the high point is a high voltage, a high potential. At the bottom point is a low voltage, a low potential. If I put a positive charge on it, it's going to go down the hill to a lower energy. So yeah, this idea of height is really, 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 really useful. You could think of it effectively, this voltage is a height map. So we're going to see, I'm going to pull up I'm going to look up some pictures online to show you this. A positive charge makes a potential that looks like a really steep hill around it. If you made this height map around a charge, it looks like a really steep hill. What happens if you put a charge on that really steep hill? You know, it's going to go down the hill. It's going to get pushed away from the charge. All right, so before we get there, though, mathematically, let's derive it. Here's the key. Remember, if you have the force between two charges, one makes the field, the other experiences the field. We used that logic last time. When we have the energy between two charges, one makes the field, one makes the voltage, the other experiences the voltage. Remember, that was the logic that we used last time with the fields. We're going to use the same logic with this energy. Okay? Go ahead and do the derivation. What is the electric potential made by a charge Q2? Remember that potential energy, electric potential energy, is K Q1 Q2 over R12. And then, yeah, you're going to use the expression I just gave you. You know, V equals U over Q. Electric potential, boom. Electric potential energy. They are not the same thing. This is the other thing I really want to hammer into your head. Electric potential doesn't have the word energy, so it's not energy. Electric potential energy has the word energy, so it's energy. It has one word difference, but electric potential is not energy. Electric potential energy is energy. One, this has two words, this has three words. They're not the same thing. It's very easy, and I don't say this to insult you, it's very common and very easy to mix them up because of that one word difference. So I'm just trying to hammer it into your head. All right, so yeah, which of these is the potential made by charge Q2? Is it K Q1 over R, K Q2 over R, K Q1 Q2 squared over R, and K1 over R? This little R12 is just the distance between charge 1 and charge 2. It's just R. Just a little more formal. All right, give you all about 20 more seconds. The math here is really easy. Yeah. Yeah. Could go either way, actually. The energy is the same. But that's just for funsies. Depends which one you want to look at. One makes it, one the other experiences it, but you can go either way. Just like with fields, we could do that either way. All right, so 5, 4, 3, 2, 1. I'm about to make a statement that's going to make about 52 of you all go, oh. Which charge is making the voltage? Charge 2. As charge 2 goes up, do you think it's going to make more voltage or less voltage? More. So Q2 should probably be in our equation. It's one of those that once you hear that statement, you're like, oh, yeah. Remember, the last step of the problem-solving process is, does my answer make sense? You should always ask, does it make sense? And that's a hard question to ask, but that does check if you actually understand what you're doing and why and things like that. So I don't say that to insult you. I just say it's a really important step to do. When you make a product, you need to evaluate whether it's what you actually want at the end. All right, so how are we going to get there? Remember, if I want the voltage made by charge 2, voltage, electric potential, same thing. These are two words for the same thing. Two phrases for the same thing. Voltage due to charge 2, the electric potential due to charge 2, is the energy of the whole system divided by the charge that's in the system. Charge 2 makes the voltage, charge 1 experiences the voltage. One makes it, one experiences it. So we get K, Q1, Q2 over R divided by Q1. Q1 cancels. And we're left with an expression that makes sense. As Q2 goes up, it makes a bigger voltage. And again, this idea of potential, we can think of the Earth and the Moon. The Earth makes a gravitational potential around it. The Moon makes a gravitational potential around it. The Moon is in the Earth's gravitational potential, so there's an energy, but also the other way is true. The Earth is in the Moon's gravitational potential, so it gets an energy, and it goes both ways. The more mass you have, the more energy you get. The more charge you have, the more energy you get. And that goes, you have more charge, bigger voltage. More charge, you also will get more energy in the same voltage. You know, both ways. It goes both ways. You all can see that with the energy. Q1 times Q2. It doesn't matter which one's first. But yeah, in this case, I asked for the voltage made by charge 2. So it needs to have a charge 2 in it. Oh, it's 53 people. That's all right. All right. So, I don't know why it says 2 2. There's just one. So the electric potential is the change potential energy experienced by a charge at test charge 1. So it is KQ over R. You just derived that. That one you're cool with. This expression here, I'll clarify. This one's going to be really easy to derive. Remember that delta V, I just wrote it as V before, but it's always a change. Equal delta U over Q. Remember that delta U was the integral of Q times the integral of V dot dr. So if I divide by Q, there you go. We have two expressions here. One is the voltage due to a point charge. The other is the change in voltage across an electric field. If we don't know what's causing that field, that's fine. So, there you go. So that's this voltage, and again, we're going to think of it like height, and I'm going to steal a picture from online to show you all this. I wish I had one in here, but sadly, I didn't put one. Okay, I did put one. I'm going to jump down to it. I do have one down here. It's just farther than I'd want it to be. And this will remind you all from the physics, if you've done the labs, this will look familiar. So, grade, there's all that stuff. We're going to be using that. Electric potential is not electric potential energy. This has the word energy. This does not have the word energy. It sounds obvious right now, but you will make this mistake. So I'm just trying to say it like 15 times to reduce how many people will make that mistake. But it's going to happen to you. And think of it like height. So this right here is what the electric potential looks like around a point charge, a positive charge. If we thought of it like a map, like a height, this is what the voltage, the electric potential looks like around a point charge. It's kind of this steep hill. Why is it useful to think of it like height? What would happen If you all saw this picture and you saw a ball on it, what's that ball going to do? Roll down the hill, all right? That is the exact same thing as me asking you, I put a positive charge next to it. What is it going to do? It's going to get repelled. They match, right? They match. This is going to get pushed away, roll down the hill, and it's going to get pushed away. Here's the weird thing. What if I put a negative charge on this? Negative charges will roll up the hill. Why do they roll up the hill? And we're going to do some math to prove this. That is lower energy for them. It's really easy for me to prove that it's lower energy. We'll do some problems to prove it. As this goes up, what happens to my voltage? Does it get bigger or smaller? As you go up the hill, what happens to my V value? Am I higher up or? I'm higher up, so it's a bigger V. This charge, is it positive or negative? Negative. What's a bigger number? Negative 1 million or negative 500? Negative 500 is a bigger number. So as you go up the hill, you get a bigger negative number. A bigger negative number is a smaller number. So it's a lower energy. So it's still obeying the rule that it goes to lower energy. You're going to see that later. But this is what I want you all to think of when you think of charge. When you think of voltage, think of it like a height map. And this is this whole equipotential. Basically, if you drew this from above, we use something called contour lines. And if you're like, what are we call them equipotential lines, but contour lines is something you all have seen before. If you've ever looked at a map and there was mountains on it, none of the maps you all are buying are three-dimensional because that's expensive. You buy a sheet of paper and it's got a map on it. How do they represent mountains? How do they represent a change in height on a mountain? They draw these circles around it where everywhere on that line is the same height. And the closer those lines are together, the steeper it is, because the height changes more rapidly. The farther apart they are, the less steep it is, because the height changes less rapidly. We can do the exact same thing with voltages. We call these equipotential lines. In the field, and this is what you all did during one of the labs, the field is strongest where the voltage changes the quickest. Just like, water is going to go downhill where the height changes the quickest. Same logic. Voltage and height. If you're cool with height, you can be cool with voltage. It's the same thing. And we're going to be leaning on this heavily, and I'm going to be trying as much as possible to help you understand voltage, because in my opinion, for most of you, it's probably the most important thing I can teach you in the class, considering all of you interact with voltage. You buy a battery and it has voltage. The wall outputs voltage. Everything is in terms of voltage. In fact, that multimeter that you all have been using in your physics lab, the only measurement it can actually make is voltage. Every single measurement it makes on there, resistance, capacitance, current, it's all just measuring voltage and then doing math. Voltage is basically the only thing we can actually measure. And then everything else comes from voltage, because it's easy to measure. All right. So, what is the net electric potential at the top of the triangle shown below? This triangle, we've used it for so many things. I've asked you for the force at the top of the triangle. I've asked you for the field at the top of the triangle. Now I'm asking you for the voltage at the top of the triangle. There's another one that says what's the energy at the top of the triangle too, but we skipped that one. Okay, so first question we ask ourselves, what are we solving for? We're solving for electric potential. I want you all to spend 20 seconds and see if you can write the right letter for that. What is the right variable for electric potential? The answer is V. Not U. Not U. U, that's energy. We're not solving for the energy. Yeah, it will happen to you. It doesn't say energy, so don't solve for energy. All right, we're solving for V, which is kind of like our height. How do we solve for V? This is actually incredibly simple. Voltage, if you all didn't realize this, there's something very beautiful about voltage. There's no vector symbol above it. It's a scalar. It's like height. Electric field has a vector. Force has a vector. Energy, no vector. It's a scalar. Voltage, no vector. It's a scalar. So how do I get this quote-unquote height at this top point? I'm going to label these charges 1, 2, and 3. If I want the voltage at the top, I'm going to find the voltage total. And that is going to equal V1 plus V2. And that's it. You're like, what about charge 3? A charge cannot make a voltage where it's at. For the same reason we can't make anything else where we're at. We're going to see when we look at the equation why that is, but you cannot make a voltage where you're at, otherwise you're going to affect yourself. And that's bad. All right, what's the expression for voltage? It's so easy. Due to point charges, it's KQ over R. So what's the voltage due to charge 1? KQ over R. What's the voltage due to charge 2? KQ over R. So what's the voltage at the top? Boom, that's it. That's the answer. Notice I did not ask you for the energy. And we did not therefore include this charge at all. What I could have asked you instead is, what is the energy that this charge, this one charge has? What's the energy stored by that one charge? What would the answer be then? You just take this voltage and multiply by negative 2Q. I didn't ask for that, but in case you wanted it, if you all wanted the energy that charge 3 has, you just take charge 3 and you multiply it by the voltage where it's located. And that's the energy of that one charge, Okay, last thing I want to mention real quick. I didn't state it here. If you do have negatives, they need to go in your equation. If you're finding the voltage due to a negative charge, you do need to put negatives. These are not absolute values. Do not make them absolute values. If you have a negative, you can have a negative voltage. That's fine. We'll see that next class, literally the next slide. Or 2 of them. Oh, look, negative voltages. They exist. That's fine. All right, see you all on Monday. Good luck with your studying. I'll bring note cards.